Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 4.2, the addition rule and the rule of complements. Our objectives for this section are to compute probabilities by using the general addition rule, compute probabilities by using the addition rule for mutually exclusive events, and to compute probabilities by using the rule of complements. Suppose we flip two fair coins. We're going to construct a tree diagram for the outcomes, answer what is the sample space, answer what is the probability of the coins being different, and finally answer what is the probability of the coins being the same. First, we need to construct the tree diagram. We start at a starting point that we just call start, and this is where we haven't flipped any coins. And then we flip a coin. It can either come out one of two things, heads or tails. Let's assume the first coin flip came out heads. So we flip a second coin. It could either be heads or it could be tails. But what if the first coin flip came out tails? Well, we'd still flip a second coin that could either land heads or tails. So our possible outcomes for the two coin flips are heads, 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 tails, tails, heads, or tails, tails. So here's our tree diagram and our list of outcomes for two coin flips. On to question 2. What is the sample space? The sample space is all the possible outcomes. So heads, 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 tails, tails, heads, and tails, tails. What is the probability that the coins are different? Well, we look at our sample space up here and we see, well, heads, tails, the coins are different, and tails, heads, the coins are different. So we have 2 outcomes out of 4 that are different, which gives us 0.5. So the probability that the coins are different is 0.5. What is the probability that the coins are the same? Well, there's again 2 possibles, heads, heads, or tails, tails. So it's 2 out of 4, or again, 0.5. So you're going to pause the video right here because this is a practice problem for you. So we're going to suppose that we flip 3 fair coins. I want you guys to construct a tree diagram, tell me what the sample space is, tell me what is the probability of all the coins being the same, either all heads or all tails, and what is the probability that all the coins are not the same, either not all heads or not all tails. So go ahead, like I said, pause the video right here, do all this, and then come check the answers. The answers will be starting in 3, 2, 1. Here on the left, we have the tree diagram, and on the right, we have the outcomes. Here we have the solution to the sample space, which is, as a reminder, just listing all of the outcomes. So heads, 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 tails, etc. What is the probability of the coins being different? So if we look, we see we have heads, heads, tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, and tails, tails, heads. So that's 6 different outcomes out of the 8 that are different, that don't have all heads or all tails. So the probability of the coins being different is 6 divided by 8, which is 0.75. What is the probability of the coins being the same? Well, we see that there's heads, 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 and tails, tails, tails. So that's 2 outcomes out of the possible 8 where the coins come up the same. So our probability there is 2 divided by 8, which is 0.25. Hopefully you guys were able to get those and you feel comfortable with this. Here's our first example. 1,000 adults were asked whether they favored a law that would provide support for higher education. In addition, each person was classified as likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to vote or favors the law? So first we're going to calculate the people that are likely to vote. There was 339 that favor, plus 289 that oppose, plus 101 that were undecided, which gives us 729 people who were likely to vote. So the probability of being likely to vote is 729 over 1,000, which is equal to 0.729. So now we're going to figure out what is the probability that somebody is likely to favor the law. So the people that favor the law, we had 339 that favored the law that were likely to vote, and 128 that favored the law that were not likely to vote, which gives us 467 people that favored the law. So the probability that they favor the law is 467 divided by 1,000, which equals 0.467. So the number of people that are likely to vote and who favor the law is 339. We have to keep track of that because we've counted those people twice. As you can see, we counted them once here as the people who were likely to vote, and then we counted them again as the people who favored the law. So since we've counted them twice, we have to subtract them out once, so that way we make sure we only count them one time. So the probability that somebody is likely to vote or favors the law is 0.729, the probability that they're likely to vote, plus 0.467, the probability that they favor the law, minus 0.339, which is the probability they are likely to vote and favors the law, because that's where we count them a second time, so we need to subtract that out, which gives us a total probability of 0.857. So the probability that somebody is likely to vote or favors the law is 0.857. Here's a practice problem for you guys. We have the same 1,000 adults, but this time we want to know what is the probability that a randomly selected adult is not likely to vote or is undecided about the law. So use the last example as a guide to solve this problem. So go ahead and do that. Pause the video, solve this problem, and the answers will be shown in 3, 2, 1. To remind you, first we need to find the probability that they're not likely to vote. And when we add all those people up, we get 271 people were not likely to vote. So the probability of not being likely to vote is 0.271. There were 133 people who were undecided about the law. So the probability of undecided is 0.133. And there were 32 people who were not likely to vote and undecided about the law. So that probability is 0.032. So our probability of being not likely to vote or undecided is the probability of being not likely to vote plus the probability of being undecided minus the probability of being not likely to vote and undecided, which is 0.271 plus 0.133 minus 0.032, which gives us 0.372. So our probability of being not likely to vote or undecided is 0.372. A compound event is an event that is formed by combining two or more events. One type of compound event is the form A or B. The event A or B occurs when A occurs, B occurs, or both A and B occur. Probabilities of events in the form A or B are computed using the general addition rule. And what the general addition rule says is for any two events, A and B, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we've seen this in the last two examples already, but this is just a general way of stating it. Two events are said to be mutually exclusive if it is impossible for both events to occur. Here's using Venn diagrams showing an example of mutually exclusive versus not mutually exclusive. So if we look at the left-hand Venn diagram, we notice that either you're in A or you're in B, but you can't be both in A and in B at the same time because they share no common space. So those are mutually exclusive events. If we look at the right-hand Venn diagram, we see that there is an area where you can be in both A and B at the same time. That's that shaded area. So since you can be both A and B at the same time, they are not mutually exclusive. Example 2. A die is rolled once. Event A is that the die comes up a 4. Event B is that the die comes up an odd number. So I want you to think about that for a second. Is it possible for a die to come up as 4 and an odd number at the same time? So go ahead and think about that. Hold on to your answer. We'll come to the solution in a second. And then the second thing is a fair coin is tossed twice. Event A is that one of the tosses is heads, and event B is that one of the tosses is tails. So now I want you to think about that. Is it possible for one of the tosses to be heads and one of the tosses to be tails? Go ahead, think about that for a second. And we're going to go to the solution in 3, 2, 1. So here's the solution. So if we think about rolling a die, if we roll it one time, is it possible to come up 4 and an odd number? Well, 4 is an even number, so it can't be both 4 and odd if we only roll the dice one time, because if it comes up 4, it's not odd, and if it comes up odd, it can't be 4. So those are mutually exclusive events. For the second one, we think of, okay, if I toss a fair coin twice, it could come up heads the first time, and then it could come up tails the second time. Okay, well, it came up heads on one of the tosses, came up tails on the other toss, so it was possible for it to happen. Thus, they are not mutually exclusive because it could have either came up heads tails or tails heads. So this is a discussion I want you to have with yourself. Just think about it for a minute. Pause the video for a minute and just think, what are some other examples of some mutually exclusive events you can think of? So just think about them. Go ahead, list some of them down here on the slide. It's just to help you think of what mutually exclusive is and just practice a little bit. So go ahead and do that, and when you're ready, we'll continue on. So we're going to continue on in 3, 2, 1. Here's our third example. In a recent year of the Olympic Games, there was a total of 10,735 athletes. Of those, 530 represented the United States, 277 represented Canada, and 102 represented Mexico. What is the probability that an Olympic athlete chosen at random represents Mexico or Canada? We need to realize that these are mutually exclusive events because it is impossible for you to compete for both Mexico and Canada at the same time. You're competing for one or the other. So we're going to use the general addition rule first that says the probability of Mexico or Canada is equal to the probability that they represent Mexico plus the probability that they represent Canada minus the probability that they represent Mexico and Canada. Well, the probability that they represent Mexico we had 102 athletes that represented Mexico out of the 10,735. The probability that they represent Canada there was 277 athletes out of the 10,735 that represented Canada. Minus, well, we just said that the probability of them representing Mexico and Canada is impossible, so there's no people that represented both Mexico and Canada. So that is 0 out of 10,735. So our probability that you represent Mexico or Canada is equal to 379 out of 10,735, which is equal to 0.03531. So that is the probability that a randomly selected athlete will represent Mexico or Canada. If we know that two events A and B are mutually exclusive, this then leads us to the probability of A and B is equal to 0. And we can use this to simplify the general addition rule. The general addition rule for mutually exclusive events, or if A and B are both mutually exclusive, is the probability of A or B is equal to the probability of A plus the probability of B. If there is a 39% chance of it being cloudy today, then there is a 61% chance that it will not be cloudy. The events cloudy and not cloudy are complements of each other. The complement of an event says that the event does not occur. If A is any event, the complement of A is the event that A does not occur. So the notation we used to use for this is the complement of A is denoted as this A raised to the C. So that is a complement. Here's example 4. So here we're going to practice some complements. 33 students were enrolled in a statistics class. Find the complements for each of the following events. Exactly 3 of them are art majors, more than 3 are art majors, at least 3 are art majors. So we're going to find those 3 complements right now. So we're going to work on the first one. Exactly 3 are art majors. So the complement would be, we want the opposite of that, is the way I like to think of it. So if exactly 3 are art majors, we want everything but 3. So we're going to say the number of art majors is not 3. That covers everything else but 3, which we want the complement to do. So the second one, more than 3 of them are art majors. So we have to think more than. So is 3 included? No, it is not, because it's more than 3. So we want 3 and everything below 3. So the complement is the number of art majors is 3 or fewer, because that covers 3 and everything below 3. So for the last one, at least 3 of them are art majors. So we have to think again, at least. Does at least include 3? Yes, it does. So 3 is included in at least. So the complement for this is the number of art majors is fewer than 3. So because again, we don't want the complement to include 3 because our original statement included 3. So that's the way we have to think of this. So I'm going to kind of draw you number lines for each one to see if that helps as well. So for this one, we have right here, we have just 3 by itself. So here's 3. And we want a statement that covers everything but 3. So that's why we did this and this right here. The number of art majors is not 3. See, we've covered everything but 3. So now we're going to do the same thing for the second one. Again, here's 3. And our statement is more than 3 of them are art majors. So 3 is not included. It's everything above 3. More than 3 are art majors. So our complement here in green, we need to include 3 and everything below that, and that's how we get 3 or fewer are art majors as a complement. Last one, we had at least 3 were art majors, so we draw our number line. Here's 3 again. So in red, we're going to draw our statement at least 3, so 3 was included, and everything more than that. So our complement had to include everything else, which is down here, which is fewer than 3. Example 5. According to the Wall Street Journal, 22% of cars sold in a recent year were small cars. What is the probability that a randomly chosen car sold in this year is not a small car? The probability of not a small car is 1, the probability of everything, minus the probability of a small car, which is equal to 1 minus that probability of a small car was 0.22, which is equal to 0.78. So the probability of not being a small car is 0.78. General rule for the rule of complements is the probability of a complement is going to be equal to 1 minus the probability of A, which we saw in the last slide.